All right, let's just dive right into this. Have you ever actually stopped to think about how incredibly weird wireless charging really is? I mean, you take your phone, you drop it on a little plastic pad, and suddenly it's just pulling power out of thin air. It genuinely feels like this invisible hand is just reaching up and pushing electricity straight into your battery. There are no exposed metal contacts, no annoying plugs to perfectly align in the dark, no tangled cords. It just happens. It feels a lot like magic. But, as we're going to see today, it is actually a beautifully elegant piece of physics that we use every single day.
So the absolutely crucial question here is, how does electricity actually jump through thin air? To get from the magic of this invisible power transfer to the actual nuts and bolts of how it works, we really need to leave the complex, boring textbooks behind. Today, we're going to break this down using a super simple everyday analogy that will totally make this technology click for you, regardless of your technical background. We are going to talk about water, fans, and windmills. But first, let's quickly cover the formal term for this invisible hand. It's called electromagnetic induction. This fundamental principle was actually discovered way back in 1831 by a guy named Michael Faraday. But honestly, let's just ditch the academic jargon for a second. Imagine for a moment that electricity is water flowing through a pipe. In our simple analogy, electromagnetic induction is essentially using a fan to create a strong gust of wind, and then using that wind to spin a windmill on the exact opposite side.
So think about the copper transmitter coil that's hidden inside the charging pad sitting on your desk. When you run an electric current, which is our water, through a tightly coiled conductor like this, it transforms. Thanks to a cool scientific principle called Ampere's law, the copper coil acts exactly like a fan. But instead of blowing normal air, it blows a magnetic field. It essentially creates this fluctuating, completely invisible dome of magnetic energy right above the pad. And that dome, well, that's our wind. Now, what exactly happens when we bring a second coil into the mix? This second one represents what is actually hidden inside the back of your smartphone. This is the receiver coil, and for our analogy, it acts exactly like a windmill. According to Faraday's law, when that magnetic field, the wind from the very first coil, pushes up against the second coil, it forces the electrons inside the copper to start moving. The wind spins the windmill, and that spinning motion creates a brand new flow of electricity, or water, right inside your phone. No physical cables required whatsoever.
And you know, this brilliantly illustrates the entire four-step inductive process. Let's just quickly walk through it together. Step 1 is the power supply. Water flows from your wall outlet straight into the charging pad. Step 2 is the creation of the electromagnetic field. The copper coil in the pad acts like a fan, using that power to whip up an invisible magnetic wind. Step 3 is the induction of current. You place your phone down, and the windmill inside catches that magnetic wind, spinning up a brand new electrical current. And finally, step 4, conversion and charging. That newly generated water flows straight into your phone's battery.
But there is a slight little catch in step 4. The electricity that's being pushed around by our magnetic wind is what's called alternating current, or AC. If we go back to our water analogy, AC is like water violently sloshing back and forth inside a pipe. Your smartphone battery absolutely cannot handle that. It needs direct current, or DC, which is a very smooth, reliable one-way flow of water. So your phone has a tiny little component built in called a rectifier. Think of the rectifier as a one-way valve. It takes that chaotic, sloshing AC water and forces it to flow perfectly smoothly in just one single direction, becoming the nice, safe DC power that fills your battery.
So how does this actually play out in your everyday life? Well, most modern smartphones use something called the Qi standard. That's spelled Qi, but pronounced Qi. This basically ensures that a Samsung phone and an Apple iPhone can use the exact same charging pad without any issues. Typically, this system delivers anywhere between 5 and 15 watts of power. And because it relies on that magnetic wind, it can actually pass right through thin physical barriers. Standard phone cases under 3 millimeters thick are completely invisible to the magnetic field. However, if you have a metal case, a super thick rugged case, or one of those magnetic card holders on the back, it acts like a solid brick wall. It physically blocks the magnetic wind from ever reaching the windmill inside your phone.
All right, now that we've totally mastered the desktop charging pad, let's completely blow the scale up. We are taking this exact same wind and windmill technology, and we're applying it to electric vehicles. Just imagine pulling your car into a parking space at the grocery store and just walking away while the car literally charges itself wirelessly from a pad embedded right there in the concrete.
But let's be real, parking a 2-ton car perfectly over a small pad is a lot harder than dropping a phone on a desk. Standard inductive charging requires precise alignment. If your phone is even slightly off-center, the windmill completely misses the wind. So for EVs, the industry shifted to a really clever variation called magnetic resonance charging. By tuning the transmitter and receiver with capacitors to a very specific resonance frequency, which is usually 85 kHz, they create a much larger, way more forgiving magnetic field. It basically means you don't have to park flawlessly, and the power can easily bridge a much larger air gap between the ground and the bottom of your car. And the power levels we are talking about here are just staggering. Remember how your phone takes about 15 watts? Well, commercial wireless EV chargers can push a massive 22 kilowatts. That is 22,000 watts of power jumping straight through thin air. To put that into perspective, it is enough to take a half-empty 60 kilowatt-hour car battery and completely top it off in under 90 minutes. And the tech isn't just stopping at grocery store parking lots. We are already getting a really fascinating glimpse into the future of dynamic charging. Detroit has actually built a 400-meter test road right here in the US, with electromagnetic coils installed underneath the actual asphalt. The idea is that your car's battery could be charged inductively while you are actively driving down the highway at speed. It could completely eliminate range anxiety, because the road itself constantly supplies the magnetic wind to your vehicle.
Okay, so we've scaled way up to massive cars and highways. Now let's scale all the way down to the absolute micro level, the human body. Wireless charging is actively revolutionizing medical implants. Think about pacemakers or left ventricular assist devices, which are essentially mechanical heart pumps. Historically, powering these meant running physical wires out through a patient's skin, which carries a massive, constant risk of severe infection. But because magnetic fields safely penetrate human tissue, just like a thin phone case, doctors can now charge these life-saving implants completely wirelessly. It is the exact same technology, literally saving lives, just by getting rid of the cables.
So the whole wind and windmill analogy of electromagnetic induction is incredible, but it definitely has one major limitation: distance. The magnetic wind dissipates very, very quickly over just a few centimeters. But back in 2012, a company called YCharge decided to break the rules entirely. They just ditched the wind and windmill analogy completely and instead adopted what's more like a flashlight and solar panel approach using infrared lasers.
The fundamental difference here is all about range. While inductive coils give you short-range power using magnetic fields, Y-charge lasers offer true room-scale distance using infrared light. Instead of converting electricity into a magnetic field, the Y-charge transmitter actually plugs into your wall and converts the electricity into a highly focused, completely invisible infrared laser beam. It quite literally shoots power across the room.
So the really crucial point is how this laser system actually operates. The receiver on your device is essentially a miniature photovoltaic cell, basically a tiny little solar panel that catches the laser and turns it back into electricity. And if you're suddenly worried about invisible lasers shooting all around your living room, don't be. It operates under extremely strict Class 1 safety standards. If a person, a pet, or literally any object breaks the beam, the system automatically shuts off in an instant. And because the beam doesn't diverge much, it can deliver several watts of power from meters away. The only real catch, it strictly requires a direct line of sight. You definitely can't charge a phone that's hidden in your pocket.
Which brings us to the real elephant in the room for all of these technologies. We absolutely love the convenience of ditching our physical cables. But that convenience definitely comes with a cost, and it's a cost dictated by the fundamental laws of physics. Whether you're using a magnetic windmill or a futuristic infrared laser, transferring energy through the air is simply not perfectly efficient.
Prepare yourself for this number: 30 to 40%. That is the massive amount of energy that is completely lost when you use a standard wireless charging pad compared to just grabbing a cable and plugging your phone in. Because our magnetic wind is blowing out in this wide dome shape, not all of it actually hits the little windmill inside your phone. A huge chunk of that energy just dissipates right into the surrounding air as pure waste heat. When you really compare the hard numbers, the reality kinda sets in. A traditional wired charger is actually incredibly efficient, usually sitting somewhere between 85 and 95%. But inductive wireless charging, it drops that efficiency all the way down to 60 or 70%. And it gets even worse. If you happen to misalign your phone on the pad by literally just 3 centimeters, the power transfer drops even further, and even more energy is just wasted as heat, unnecessarily warming up your battery and the room around you. Sure, on a single phone charge, this is just fractions of a penny on your electric bill. But scale that waste up to billions of smartphones and eventually millions of electric cars all over the world.
So I'm going to leave you with this final kind of provocative thought. We have clearly conquered the magic of moving power through thin air. From the simple wind and windmills charging our phones on our nightstands, to massive electrified highways, to literal room-scale lasers. But as our world becomes increasingly conscious of our environmental footprint and the need for energy conservation, we really have to ask ourselves a pretty tough question. Is willingly throwing away 30% of our energy actually worth the ultimate luxury of just never plugging a cable in again? It is a fascinating trade-off between absolute convenience and optimal efficiency. Thanks so much for joining me on this explainer, and definitely keep questioning the magic behind your everyday tech.